Our first presentation will be from Dr. John Hildreth on quality monitoring of engine oils for equipment on extended drain intervals. Dr. Hildreth is an associate professor in the Department of Engineering, Technology, and Construction Management at the University of North Carolina at Charlotte. His research interests include modeling and management of construction equipment and fleets, construction operations, design, analysis, improvement, and virtual and simulated construction environments. He holds BS and MS degrees in civil engineering from West Virginia University and a PhD in civil engineering from Virginia Tech. He has 8 years of experience in the engineering and construction industries, and I know John's very active in all of the things that we are trying to do in the way of maintenance equipment. So, John, I'll turn it over to you.
Still in. Thanks, Danny. Thanks you guys for getting up this morning and being here. I'm going to talk to you about a project that we're doing currently with the North Carolina Department of Transportation. And so you see that Scott Capps, who is the state maintenance engineer and the fleet manager there, is co-author on this, as is Newell Brooks. Scott claims his travel wasn't approved, so he's not here. We're going to give him all the questions. And Newell must have retired just to get out of this, I don't know. But they left me here. Now, those guys have been really good to work with over the years. And we were sad to see Newell go, but he just retired. If you know Newell, he was very active. So we're going to talk about this project we're going through. We're going to do it in a few stages. It looks long. It won't be nearly that long. We'll talk a little bit about engine oil and what it is and what it does and how it changes as we use it through the life of the engine. We'll look at what we're trying to achieve in North Carolina, what we did, what we got, what we're drawing from that, the conclusions, and then for sort of future work is where we're currently going. So the future is now, so to speak. So you guys are all familiar with oil, but just to lay a baseline here, two types, right? There's your conventional mineral oil derived from crude, and then there's the, I'm not even going to try it, PAO, synthetic oils that are manufactured, so to speak. And just derived from a different base material. And then from that we shove in additives for any number of purposes, either to reduce friction or to increase or decrease, to set the viscosity the right place, the thickness of the oil. We add stuff for lubricity, which sounds a lot like friction, but it's a little bit different. And wear modifiers so that we can impact how the wear surfaces interact with one another based on the oil, the thin film of oil. And we throw in detergents to keep those surfaces fairly clean, and dispersants to keep the stuff that comes off of that suspended in the oil and not depositing in other places. So the bottom line is this base oil has a bunch of additives thrown onto it, and that impacts how this thing changes as it ages. And so what happens as it ages? One of three things, or all three things actually, can occur, and almost certainly two of them will. The oil will chemically degrade. The chemical makeup of this stuff, it is a chemistry problem, and the chemical makeup will change. The base oil materials will react chemically with the oxygen, nitrogen, and sulfur that it comes into contact with. And as those reactions occur, these harmful compounds, and harmful sounds really bad, it's not quite that bad, but things that are detrimental, not positive for the engine, are formed. And in order to sort of slow that down or offset the impact of that, we add add in the additives, and they sort of absorb that. So think of it as a shock absorber. They'll absorb some of those chemical reactions until they run out. And so essentially we start with this reserve of additive and deplete that chemically. And so we're trying to make sure we don't get too far down that road. Viscosity can change. It doesn't have to. It doesn't always, but it's not uncommon. And we say degradation there, but it can go either way. Your viscosity is one of those things that's got to be in the sweet spot, so to speak. If it gets too thick, if the viscosity increases, that's a problem. The oil won't flow right, and that comes really from a thickening because of soot intrusion. So as this stuff, as the combustion occurs, you get some blow-by, it gets soot into the oil, causes it to turn to that nice black on the right, and can thicken the oil detrimentally. Probably more common, from an extent standpoint, is the viscosity will decrease. And that's really a function of something else getting in there. And so that's your water, that's your fuel, that's your glycol, something getting in there with a lower viscosity, thinning that stuff down, which really impacts its ability to properly coat the materials, the metals in the engine, for friction purposes. And then lastly, almost certainly to some degree, you'll have some contamination. Now, how much of that is very much engine dependent? The first two are very much measures of oil, and the third one there is very much a measure of the engine. It impacts the oil, but what it's really telling you is not how the oil is performing, it's telling you how your engine's performing. But we look at that and it can impact the quality of your oil. Of course, it can dilute, that impacts your viscosity, or you can get stuff in there. And stuff can be anything from dirt, which is very detrimental, to a lot of the wear metals. So your coppers, your tins, your aluminums, your irons, chromiums, those types of things. And so these are the sort of things that we look at as changing as the oil ages, as we run the engine with the oil in it. And so what we had to do, the first thing we had to do, because we're monitoring these oils throughout a relatively long period of time, we had to determine how bad was bad enough to change the oil. And so these are not hard and fast, but they are some pretty good ideas on where your oil quality thresholds need to be. Of course, viscosity, those numbers, 12.5 to 16.3 centistokes, that's set by SAE, that's just a J300 for 40 weight oil. That's an SAE standard, and that is for 40 weight. Those numbers vary depending on what weight of oil you have. But we're running all 40 weight oils. And so that's our viscosity. TBN is a measure, your total base number, is a measure of the ability to absorb acidic compounds, so to speak. And so the lower that number is, the less basic, the more acidic your oil is. And that really impacts the ability to offset the corrosion effect. And so that starts out, we'll see some numbers, that'll start out around 9 or 10. When it gets down to about 4, that's as low as we want to go. Now you'll see some folks, and that's really a key one. You'll see some folks that'll tell you you can go to 3 relatively easily. I agree. You'll see some folks say you can get down to 1. At some point, you're getting pretty daggone acidic, and you're going to start oxidizing the pieces inside your engine. So that's a key one, your total base number. Water content, you really can't have much. You'll probably get a little bit condensation in the crankcase and that sort of thing, but that's got to be kept pretty low. You can withstand some fuel, and you probably all have some fuel in your oil systems now. So 7%. When it comes to glycol, you really need to detect that by looking at 2 things. You're looking for the combined presence of sodium and potassium. You'll see some oil analyzers, the one we used here, we'll talk about it in a second, that actually says it measures glycol, but you don't really know what you've got. So to pick that up, you're really looking for a decrease in viscosity as well as a combined presence of your sodium and your potassium there. Oxidation and nitration levels, we can talk about those later. In terms of contaminants, you see those numbers there. My understanding, based on some of the folks I've talked to, is that really copper and aluminum don't matter, because the copper and aluminum in today's engines are so soft relative to the internal parts that it's really not a big deal. And so we've got thresholds there for copper and aluminum. Now the only caveat to that is when you have aluminum in conjunction with silicon. Because when you have aluminum in conjunction with silicon, you've got dirt. And dirt is a real problem. Aluminum is the most abundant element on Earth. And so you always get that when you get dirt. And the aluminum in the dirt is different than the aluminum in your engines. So the wear pieces that come out of your engines, my understanding is they're soft enough, they're not detrimental to it. So we've got some thresholds, but we're not paying too much attention to those. Iron's a big one, as you would imagine, and silicon, just for the presence of dirt. So we set some baseline standards of thresholds of things we're looking for and levels we do or don't want to reach. So what did we set out to do? Right now, North Carolina changes their oil on every piece of machinery that they have, either at 5,000 miles or 200 hours, or every year, or depending on who you talk to, every other year. But they sort of have a very set, very fixed, completely use independent, well, not completely use independent, largely use independent PM schedule. And so what we wanted to do was to evaluate that, essentially. And so we set out to run some of their machines without changing the oil on that schedule. Let's push them out, but let's do that carefully, and let's monitor what the oil looks like as we go, with the intent to determine rates of degradation and try to project, not necessarily project out, but find out when was the right time, and then use that info to go back and assess their existing schedule and provide any recommendations. So that was our goal. That was our objectives. We have and we continue to look at 4 different types of equipment. We're going to talk about the first 2 here. The 0209, Class 0209 utility trucks, that's the lower right. That's an International 7300. It's a standard. They use these things for all kinds of stuff. And so that's got a flatbed, but they can put any number of things on the back of those. They're running an inline 6. I can't remember I can't remember the exact number on the engine. But we got several. They got a handful of those, and then we've got a handful of these Ford F-350. We call them IMAPs, Incident Management and Patrol Trucks. IMAPs, right? Sponsored by State Farm. I get paid no extra to say that, but North Carolina I think does. And we've got several of those running. We've got some really interesting stuff in those. We're also looking at some mowing tractors, both mowing tractors and slope mowing tractors, just 2 different sizes there. We'll talk about the trucks today. So what are we doing? Well, we are collecting oil periodically. And I say periodically, we pick it up at about 1,000 miles. So once they change the oil, we get a sample at about 1,000 miles, 3,000, and 5,000. And then we're going anywhere from 1,000 to 1,500, every 1,000 or 1,500 after that. So we're picking it up as we go. Every time we pick up 3 samples, and then we're averaging those together. So all the data you see today is the average of the 3 samples that we've got at those ages. And we pull those in, and we're using an OSA 4 truck check. I don't know if you're familiar with that. It's about the only self-contained, out-of-the-box, ready-to-run benchtop oil analyzer that we can find. It's been pretty good. It's not perfect. I can talk to you about what we've learned about it if you're interested, but it's been a pretty good thing. It's been a pretty good tool for us. It uses dual atomic emission spectrometers and infrared spectrometers. Basically, it vaporizes the oil into a plasma ball and then analyzes that, and has the ability to give us viscosity at both 40 and 100 degrees C. So it's a pretty self-contained unit. We can do a sample in about 15 minutes. But we can only do about 3 an hour, because then you got to flush it and it's got to calibrate and that sort of thing. But it beats 3 weeks off in a lab, which was really the key to this. So that's what we're using. Just as sort of another baseline, we pulled some of the fresh oil, so oil that's never been in an engine. And they're using 2 types of oil in North Carolina. Everybody but the IMAPs uses the conventional Conoco Fleet Supreme 15W40. So that's everything else, which is somewhere in the neighborhood of about 8,000 machines. And so we pulled some fresh oil, and we tested 2 things, viscosity and TBN, just to see how what they were getting, because they buy it through their prison ministry or prison packaging group, to see how it compared with what Conoco says the oil should be. And you see those compared very well, right? Viscosity was 15.2 is what Conoco said, and we got 15. TBN, the higher the better. They said 9.5, we got 933. So that matches pretty well. The IMAP trucks all run a Shell Rotella T6. And when we started pulling some samples for that, we noticed that the viscosity that we were getting is substantially lower than what Shell says it should be. And 14.2 to 12.8 may not look like much right now, but when we look at a couple of charts here, it's a big difference. It's a big difference. And in fact, if you can remember back, the minimum is 12.5. And so we're running down about 12.8, close to that. And about 20% of the oil, fresh oil, never in an engine that we tested, had a viscosity lower than 12.5, which was our threshold for 40 weight oil. So we're not too sure about that. And we're starting about a point lower, which is about 10% lower on the TBN. So we don't know exactly if what's causing that, but that's certainly what we found. So in terms of viscosity, on the left-hand side, you see the Class 0209 running conventional oil. You see that we start, this is our fresh oil, these points right here, and this is what we've tested out to pretty close to 8,000 miles. You see that it's running relatively flat. We're down near the bottom, but we're bouncing around fairly spread out data, but you wouldn't look at that and say there's an issue with this oil getting old in terms of viscosity. And in fact, we've got pretty good data out to about 6,000 miles. We just have one point out here. But we don't see viscosity changing in that oil and those machines. But when you look at the synthetic oil in the IMAP trucks, the F350s, we saw a very distinct difference. And the difference really came down to which engine is in that truck. Because some of these green triangles, if you can see them, are 6.7 liter engines that are 2011, 2013 F350s. But we had some 2008 6.4 liter engines that we also had in there. And what you see is in the 6.7s, the viscosity is very much right along this bottom, not really changing out to about 13,000 miles. But in the old engine, in the 6.4, it's nowhere near a 40 weight oil. And when you're down at a viscosity of 8 or 9, that oil is no longer behaving like a 40 weight oil. And that's a result of fuel dilution. From everything the people I've talked to, the things that I've read, the things that I've seen, everyone says, yep, it's a 6.4, you've got a bunch of fuel in there. Could be a problem. But it was very interesting. It was the first piece that said, hey, there's something very different here. So that's from a viscosity standpoint. From a chemical standpoint, again, the conventional 10W40 ConocoPhillips oil, we see very little change as this oil ages. So from a chemical reserve, right, from ability to offset acidic compounds, that oil is very much flat. Small decrease, but it's very much flat throughout the age of the oil. The synthetic oil, however, again, we see a difference in the 6.7s and the 6.4s, but just the stark difference between the chart on the left and the chart on the right. The synthetic oil is depleting that additive that is used to boost that TBN and offset those acidic compounds. We do see the 6.7s performing a little bit better. I may have a better slide next. 4 is our minimum, so we're running out here in this 12 to 13,000 mile age before we hit that. It's a little tougher to see here, but the blue lines, we're probably looking more, that looks like it's going to run out here, but we don't have a lot of data here. I think we're probably looking at about an 8,000 mile, according to just TBN. We're seeing real differences just in the fact that it's changing, and the fact that we're getting differences between the engines. So I had that on there. That was just to show these are our confidence intervals, which means we would be, based on our data, we would estimate that 95% confidence that our number is going to fall between those two. And we were using that to say, okay, if it looks like we can get to 4 at 13, when are we really getting there and it's back a little bit? Pretty tight data though, really. The flip side of that is the oxidation and nitration, and I don't have this for the 0209s because there's nothing there. That oil is not oxidizing, that oil is not seeing nitration in it. But we are seeing very real differences, again, in the 6.4s and the 6.7s. And if you think about the oxidation and the chemical process there, that's probably what's driving, that and the nitration combined, is what's driving that TBN down. And so you see it's eating up those basic reserves, and you see this very steep climb in oxidation on the 6.4s to where we're crossing that threshold around about 5,000 miles. And nitration, not quite as much. I should say, if you do take a look at the paper, the data here is different. And the data here is different because we wrote the paper in August, July of last year. And what I'm showing here is updated to around about the end of November. And so this stuff looks a little, there'll be more data here. Some of this stuff looks a little different just because we've got more to show here. But again, the 6.7s are performing quite well. The 6.4s are performing okay, but they're not lasting nearly as long as what we see. So what have we pulled out of this? A couple of things. The truck check, and this is not a commercial for them at all, but it works. It's worked relatively well for us. We can run a sample, we can get a result in about 15 minutes. Before the guys are done buttoning up the truck, they know whether they need to change the oil or not, usually. And we don't always do that, but that's if it's a special case and we're watching this one and we really need to know, we can know in about 15 minutes what the oil looks like. In the group that we're looking at, we're not seeing contamination. So of those three possible things, contamination is really not an issue. We've seen very little of the wear metals. We've seen no oil or no soot really, no dirt, none of that stuff. We are seeing some fuel get in there, but really not a contamination issue at all. It is important to look collectively, comprehensively at what you get. And what I mean by that is there is no magic bullet. You can't just look at TB and you can't just look at viscosity. You can't just look at your iron. You've got to look at all of that collectively to assess the quality of what you got in terms of your oil and its performance. Our conventional oil is performing very well. They're changing it every 5,000 miles now. It's quite likely we could push that out to 10 with no issues. Maybe beyond. We're pretty comfortable with what we've got, say, in 10,000 miles. The synthetic oil, on the other hand, it is performing well. It's not as well. Very much depends on the engines that we're looking at right now. We're probably going to have to maintain the 5,000 mile change on the 6.4s. Probably can't push that out. If we could, it wouldn't be very far. But on the 6.7s, we can probably double that to 10,000 miles. So where do we go from here? We are going to engage some outside labs, or an outside lab, to measure our fuel dilution. The one drawback to the truck check is that because of the way it analyzes the oil, it can't detect diesel in the oil. The diesel and the oil are chemically, molecularly so similar that it can't tell the difference. So even though we're pretty confident that what we see there is fuel dilution in the oil, our results come back with zero fuel every time. It just can't tell them apart. So we're going to have to send that off just to determine how much fuel dilution we really have. We would also, since we're going to do that, we said, well, we ought to verify those parameters for the fresh oil on the synthetic side because they are different from what's published. We want to pull out, so I said all of the IMAP trucks run the synthetic oil, and because the conventional oil is performing so well, we said, why don't we take a couple of those and put the conventional oil in them and see what happens. If it worked, and it worked very well, they only run two products and you could eliminate one of them from the shop. No need to keep the synthetic if you can run straight conventional on everything. And then the long-term goal will be to assess not only the impacts of extending the oil economically, right? Your costs are going to drop dramatically, but also from an environmental impact. You're just not producing as much waste oil, handling as much waste oil. Okay. And with that, you want to do questions now, or you want to do them again?
Sure, we'll take a few now.
Big round numbers, 45, 50, something like that. And it's self-contained. It's a little bit wider than this podium, but it would set. I mean, it's sort of that big. Now there are some consumables that go with that. You see that jug on the side. So this, after you run some oil through here, it flushes itself, and then there's some standardization fluids to calibrate itself periodically. We run through a fair bit of this flush stuff, but we've run. We've got to be getting close to 1,000 samples through it this year.
Do you envision you'll be able to double the oil change interval in the equipment?
We're not sure. Well, on the tractors, yes. What we've looked at so far is just the tractors, mowing tractors. Yeah. That data looks a lot like what we see for the 0209s. From a TBN perspective, except we see a little bit more decrease, but it's still very flat. Yeah, yeah.
Did NCDOT change their service hours as a result of this?
Not
study?
yet. We're still. I mean, so this study itself runs through August of this year, and we'll wrap it up. And we're looking at another project to go to another part of the state and look at a different set of equipment to sort of continue this and broaden it out. In the back?
Is mileage the best way to measure wear on the oil? Because I imagine different size vehicles are used differently. So
I agree. Is it the best way? No. Yeah, I mean, I think if we really wanted to get down to engine load, right? Phil could probably tell us better, but you would measure RPM seconds or something, right? And I'm not sure whether it's an RPM second or whether it's a degree second, whether you're looking at engine temperature. Maybe you need a combination of those two. But it's easy to get, right? And it beats the heck out of a calendar. I think, and one of the things that we're going to do this spring that wasn't listed there, I think a surrogate for miles driven can be fuel through the engine. And so we have the data to dig back through and get gallons of fuel burned at each of these and turn measure age that way, which is not as good as the degree seconds, but it's probably better than miles, particularly on the trucks, because these guys idle a lot, right? We capture some of that in the mowing tractors because it's an hour meter, but not here. Good question. That's it. You guys are easy.
Thank you, John.
Thank you very much.